Well,
Want to try?
the crestron seems
The
promising.
crestron seems to be the.
Yeah, that's cool.
Yeah,
There we go.
it's working.
Okay.
Some reminders, I'll start with that,
Mm-hmm.
and then I'll hand it to you,
Okay.
and then you'll hand it back to me.
Good.
I'll run Q&A.
Mm-hmm.
I'll repeat everything, every question, so I'll interrupt you. Um, Even though you have the microphone, really project
Yeah.
and make sure when you move, the mic moves with you.
This could be the hardest part.
Yes. Yeah.
Um,
I think that's it. We'll start at not looking great for observing.
okay.
So I thought it was getting a little better. I thought so too, but it looks a little more cloudy, but on the forecast, it's literally clear every hour except the two that hour.
Speak something in the mic, and I'll use.
Okay.
I'll,
So,
It feels, it is always feels like this every single semester. Never purify for the fall. Just try for that Tuesday.
well, I think it's like oh, with Fred.
Amazing.
Thank you.
yeah, could you do the test?
Oh, just of this mic.
Right, testing.
Should I keep this here or should I put it on? Maybe. Is this the optimal laptop placement?
It's totally up to you.
Maybe I'll just keep it here.
You're welcome.
Okay, I think we'll go ahead and get started. Can everyone hear me okay? Awesome. All right, my name is Amanda. I'm an instructor here and also the coordinator of outreach. I'm so excited to have you all with us tonight, especially since we don't know if we're going to observe or legend was you had to sleep with your pajamas inside out and backwards, put a spoon under your pillow, and flush ice cubes down the toilet. And I feel we all need to be doing the opposite of that before these observing nights so that we can have clear skies. It's still not looking fantastic, but the observing team is really itching to observe, so they're going to be looking at the sky up until the end of the talk, so it will truly be a game time decision. But whether we observe or not tonight, we have a wonderful talk, and I'm really excited to learn about magnetic spheres and magnetic fields. Most astronomers totally ignore them because they're really complicated, so I don't personally know a lot about them. All right, we're going to start with trivia. I'll talk about our summer schedule, then we'll have our fantastic talk, not all number ones. Then we'll do Q&A and maybe stargazing/observing. All right, so our trivia, the way this is going to work is I will give you a question. I'll have you think about it and talk with others. Collaboration is very important in science. And then I'll say 1, 2, 3 votes, and you'll show 1 for A, 2 for B, 3 for C, 4 for D, and you can do a combination, hint, hint. All right, question number 1. What is a result of the Earth's magnetic field? We've already got an answer. Okay, I hear some good deliberation. Let's share our answers. 3, 2, 1, vote. All right, I see 3s, I see 4s, I see a 2. I don't think I see any 1s. Well, the answer is C, to reflect energetic particles from the Earth. So we can thank our magnetic field to keeping us safe from higher radiation. Question 2. How strong is the magnetic field of a sunspot? I'm going to give you a little bit more information for this one. Magnetic fields are in the sun. So where these freckles are, much more magnetic than where they're not. They're also a small part of the sun's surface, but they're huge. This is about the Earth to scale to one of these sunspots. All right, so now that you have a little more information, think and talk amongst yourself. How magnetic is one of these spots? Okay, let's see those answers. 3, 2, 1, vote. I see 4s. I see 2s. Do I see a 3? Do I see a 1? No, mostly 4s. That's what I thought too, but no. I had to triple check my math on this because I was like, no way that's right. but it's actually not very strong. So a bar magnet, you can think of like a fridge magnet. Maybe you even have 30 magnets on your fridge. You've made a sunspot. Congratulations. All right, question number 3. Which animal can sense magnetic fields? Thank you. Used it 4 times. Okay, 3, 2, 1, vote. All right, I'm seeing 1s, 3s, 4s, 2s, and collectively you are correct. It's all of them. And these aren't even all of the animals that can sense the magnetic fields. Humans really are missing out. A lot of animals use it to migrate. So think about animals who have really long migrations. How do they know where they're going? Some of it is being guided by the Earth's magnetic field lines. All right, question 4. What is a magnetar? Okay, 3, 2, 1, votes. I'm seeing 1s, 4s, 3s. Do I see any 2s? No? All right, the correct answer is a neutron star with an incredibly strong magnetic field. Some could be a piece of science fiction. It also highlights how astronomers are not very creative at naming things. They found something that's very strong magnetically, so they called it a magnetar. All right, our last question for the night is which planet or planets don't have a significant magnetic field? We already learned our Earth has one, so it's not on this list. All right, 3, 2, 1, vote. You can use more than one hand. It's hard. We need to be like some kind of creature that has many arms and many fingers. All right, it is Venus and Mars. So they probably had a magnetic field at some points, And over time, due to factors I'm not going to get into, the magnetic field went away. All right, a round of applause for everyone. Okay, our announcements. We will be having talks over the summer. We'll have one June, July, and August. We don't know the schedule just yet because Columbia needs to release the classroom so we can reserve this one. We're aiming for our first one to be at the end of June. As always, we'll send out announcements 2 weeks before the event, and our mailing list is the best way to find out about the events. But until then, we have a fantastic talk with our speaker, Ryan Goland, on magnetic fields. So I'm going to let him take it from there.
Thank you. Okay, well, first a fun fact about me. I really like moving my arms when I talk, so this is going to be very difficult to keep the microphone in front of my face for the next 30 minutes, but wish me luck. So I'm Ryan. I'm a final year PhD candidate in the Columbia Astronomy Department. And today I want to take you on a tour of our magnetic universe to illustrate the crucial role that magnetism plays in shaping our cosmos. But before we get into any astrophysics, I just want to take some time to appreciate the intimate relationship we have with magnetic fields here on Earth. We interact with magnetism every day of our lives. So does anybody want to volunteer an example of how we interact with magnetic fields here on Earth? Yes. Yes, compasses? Any other? Yes? Charging phones, yep. Yeah. Yeah, credit card scanners. One more. Yep. Yes, electric cars. Great. All fantastic applications. A few that I thought of where magnetic fields are essential for generating electricity to power our homes, to power cities, our entire world. Similarly, electric motors spin because of magnetic fields, so powering electric cars. The hard drives that store memory on our computers and other information technology are fully built from magnets and magnetic fields. And also a wide swath of medical imaging technology, like MRI machines, use heavy use of magnetic fields. But despite us being surrounded by magnetic fields here on Earth, the one thing I want you to take away from this talk is that magnetic fields are not exclusive to our Earth. Magnetic fields are everywhere throughout the universe, and I mean everywhere, and they shape our cosmos across all scales, from the scale of the smallest planet to the scale of the most massive cluster of galaxies. And by leading you on a tour of our universe, I'm going to prove that both of these statements are absolutely correct. But I do want to start with some prerequisites to make sure we're all on the same page. Because while we are probably intuitively familiar with how magnetic fields work, what they do, I think it's good to establish some rigorous definition of what is a magnetic field to guide us through the next 25 minutes or so. So I think a great working definition of magnetic fields is that a magnetic field is a force field generated by electric current that deflects electrically charged particles. So there are three parts to this definition, and I'll break it down into all three. Starting with a magnetic field being a force field, or technically what's called a vector field. Because at every point in space, we can assign both a strength and a direction to this magnetic field. So we can draw a little arrow that we call a vector. And the strength and direction of the magnetic field at a point dictates how the magnetic force behaves at that point. But it can be a bit cumbersome to draw out all of these tiny arrows. So us physicists like to take a shortcut and draw what are called magnetic field lines just by playing connect the dots. I drew these field lines myself. As you can tell, I'm an excellent artist. And we have the same information here as we had in the vector field with the magnetic field direction indicated by the arrows. But now the strength is indicated by the density of the field lines. The closer together the field lines are, the stronger the magnetic field is in that region. So usually this magnetic field line formalism is just a mnemonic or some useful time-saving tool. But in astrophysics, as we'll see, these magnetic field lines take on a role of a real physical object. And this is because of this second part of the definition of a magnetic field. A magnetic field deflects charged particles. So what does this mean? If we were to fire a positive charge and a negative charge, say a proton and an electron, into a magnetic field, the magnetic force would change the direction of that charged particle, but it would not change its speed. So what ends up happening is that these charged particles gyrate around magnetic field lines and end up being tied to these field lines, and these field lines act as a sort of guide to the trajectories of these charged particles. So this gives some very interesting physical properties to the field lines themselves. For instance, once these particles become tied to the field lines themselves behave like almost taut strings or tensile strings, where if you try to stretch the string or the field line, or try to deform the field line, it'll just snap right back to where it was before. These field lines do not like to be deformed or manipulated. But there's a third part to our definition, that magnetic fields is generated by electric currents. So here on Earth, it's very easy to generate an electric current. We just take a battery, hook it up to some wires, we get a flow of electrons, and we have a current. But what supplies this current out in space? Because I don't think there are any Duracells or energizers floating around in interstellar space. I could be wrong, but for now, we'll just assume that there are no batteries out in the universe. So maybe, does anybody want to guess what might supply the current out beyond the Earth in order to generate these magnetic fields? Sorry? Oh, light, not quite. But. So the answer here is the fourth state of matter, plasma. So you may have heard of plasma being referred to as the fourth state of matter alongside solid liquids and gases, or you may have heard that plasmas fill almost the entire universe from the least dense regions to the most dense regions, accounting for 99.999% of the luminous mass of our universe. And plasmas and magnetic fields go hand in hand. So I want to spend a little time diving into what makes a plasma a plasma. A decent definition of a plasma, for our sakes, is that a plasma is a gas of electrically charged particles. So right now, we're breathing atoms where the charges in these molecules and atoms cancel out, so there's no net electric charge. But if we were to superheat the gas around us, these molecules would start breaking apart, the atoms would start breaking apart, and instead we'd get this soup of free positive charges and negative charges. In an atom, the positive nucleus would be separated out from the negative electron, and we'd get this gas of free-floating electric charges. And so I put gas in quotation marks because, yes, plasmas do share a lot of properties with neutral gases, but they're also so much more. Because they're comprised of electric charges, unlike neutral gases, plasmas can conduct electricity, they can supply currents, they can generate magnetic fields, and most importantly, they can both manipulate and be manipulated by magnetic fields. So ultimately, plasmas and astrophysical magnetic fields are interdependent. You can't have one without the other in multiple ways. So all these clouds of plasma that we find floating around the universe have these magnetic field lines embedded in them. If you try to along with it as well, these two entities are coupled together. They're frozen into each other. And not just that, but as we said before, the magnetic force gives these field lines an effective tension, like a taut string or a rubber rope that resists the deformation induced by the plasma. And these field lines exert a pressure on their surrounding, pushing away the plasma that they're embedded in. So out in space, in these astrophysical systems, we get this rich interplay between these flowing electrically charged plasmas and these rubbery, resistive magnetic field lines. Ultimately, you can't study astrophysical magnetic fields without plasma physics. So now we have all the tools necessary to understand, to quantify, to model magnetic fields throughout the universe. But before I take you on the tour of our magnetic universe, I do want to stop and check your understanding with a little pop quiz. This one's a little tricky, but where do plasmas play baseball? What was that? Yes, they play on the magnetic fields. And believe me, the jokes are going to get much worse. So, yeah. So now let's just start at home and move through the universe and see what these magnetic fields are doing. So Amanda and I were apparently on the exact same wavelength, and we took the exact same image from Google Images to represent our Earth's magnetic fields, which the Earth generates itself and sustains itself. And we are intimately familiar with this field. It's what allows compasses to point, it allows birds to navigate, sea turtles to migrate. As Amanda said, there are a whole slew of animals on Earth that have this innate sense for the Earth's magnetic field. There have been a number of studies of sea turtle migration that show that as sea turtles move from coast to coast, they trace out the magnetic field lines of the Earth. I'm kind of disappointed that humans were skipped over in this evolutionary trait. Seems fun to be able to detect magnetic field lines. But I think it's just very cool that our own Earth's magnetic field is baked into the biology of so many organisms here on Earth. Another cool thing about the Earth's magnetic field is that it allows us to probe the interior structure of our Earth and the formation history of our Earth. Because we believe that the magnetic fields of our Earth is produced by this churning of molten liquid or molten metal in the outer core of our Earth. So this isn't a plasma, but it has the same properties of a plasma because it conducts electricity and it flows like a fluid. So when the Earth rotates, we end up getting this churning molten iron and nickel that continually supplies electric currents, continually sustains this large-scale magnetic field in what's known as a dynamo process. A very cool word. And these dynamo processes aren't just local to our Earth. We also believe that the sun's magnetic field is generated by a dynamo, that the galaxy's magnetic field is generated by a dynamo, by this twisting of magnetic field lines. But this also raises another important question that we saw in trivia. Why do only some planets and some extrasolar planets have magnetic fields? Why do only some planets have dynamos? This is still an open question. There's magnetic fields in planetary bodies, in asteroids, in planets outside of our solar system to, one, get a sense of the interior structure of these planets. We can look at exoplanets outside of our solar system millions of light years away, and by detecting their magnetic fields, we can say something about the interior of these distant planets. We can also say something about how these planets formed, and by looking at the planetary or the magnetic field signatures of multiple planets, we can get a sense of how a solar system as a whole formed. So this is all very cool, very nice science, but we would not be able to do the science without our Earth's magnetic fields. The magnetic field is essential for life, as Amanda also said in the trivia. The sun is constantly bombarding the Earth with high energy light and radiation and hot plasma. And if it weren't for the shields that our magnetic fields presents, we would turn into what scientists call toast. And that's what happens with Mars. Mars does not have a persistent magnetic field, so the sun just stripped its atmosphere. And this is one of the reasons why it's nearly impossible up terraforming Mars. Just tell him he forgot about magnetic fields. Simple as that. But yeah, without this shields, we would not be here. Sort of an ironic thing about this is that the same radiation and plasma that our Earth's magnetic field shields us from is launched by magnetic fields on the sun. So stars, like our sun, are nothing more than huge blobs of plasma teeming with magnetic fields. And basically, all the surface features, all the explosions, all the outflows from our sun are caused by magnetic fields. So for instance, magnetic fields are responsible for sunspots that we just saw, are these Earth-sized dark spots on the sun that are also associated with the solar prominences, these arcs of plasma coming out of these sunspots. And one of the major achievements of 20th century plasma astrophysics was linking these two phenomena via magnetic fields. So I said earlier that magnetic fields exert a pressure on their surroundings. And this allows magnetic fields to become buoyant. So we see that as this plasma becomes buoyant and rises above the surface, we get these prominences. And at the foot points of the prominences, we get these dark, cold sunspots. And this is because the magnetic field is tensile. As I said, it behaves like this taut string that resists the flow of plasma up through the magnetic field. So hot plasma can rise everywhere else in the sun, but not in these regions of strong or relatively strong magnetic fields. So these sunspots are cold, they're large, they're dark, but they have very strong, in an astrophysical sense, magnetic fields. And as these prominences rise more and more and more, they start to get distorted by random motions on the surface of the sun. And they can, these magnetic field lines can disconnect and reconnect in this explosive process called magnetic reconnection. And I want to play this video from NASA where they explain magnetic reconnection much better than I can. And let's see if we have sound. We do. Okay. So here's where these prominences are being folded together, and oppositely directed magnetic field lines are going to squish together. Great. So magnetic reconnection is widespread on the sun, but also widespread throughout the universe, and produces these high energy explosive events almost everywhere. But when it comes to geomagnetic storms in the atmosphere of our Earth, when these high energy blasts of radiation and plasma hit our atmosphere, mess with satellites, mess with electrical grids, with radio communication, even aurorae are generated by these explosive events when the mass or matter from the sun is blasted right into our atmosphere and ionizes the upper atmosphere at the poles. So before we move on, I want to check your understanding again, thinking back to all the magnetic fields in our sun. This is another tricky one. What's the sun's favorite board game? And I told you these jokes do get much worse. Any guesses? Yes. Close. It's Reconnect 4. Fantastic. I wish that were a real game. But, okay, so we've talked about planets, we've talked about stars, but what about the magnetic fields around the remnants left behind by dead stars? It turns out that the magnetic fields around dead stars produce some of the universe's most exotic and energetic phenomena. So we know that stars can die in a number of different ways. Our sun, in about 5 billion years, will pretty gently collapse into what's known as a white dwarf. But more massive stars will explode in a supernova and collapse extremely violently into what are known as neutron stars or black holes. And so if the progenitor star that's going to collapse well, stellar collapse, plus this vigorous dynamo action inside of the star, significantly amplifies these magnetic fields, leading to these super strong, super exotic magnetic fields. So, for instance, neutron stars are the strongest magnets in the universe. We have two flavors of neutron stars. We have the pulsars, a great name because they pulse, where their magnetic fields are up to 1 million times stronger than the strongest magnetic fields on Earth. And the combination of the rotation of these pulsars with these strong magnetic fields funnels this high energy focused radiation into these narrow, intense beams that makes these pulsars look almost like lighthouses to us observers on Earth. And this pulsation, this rotation is so precise, we can use these pulsars almost as clocks. But we also have the more extreme cousins of the pulsars, the magnetars, also a fantastic name, where the magnetic fields can be up to 1 billion times stronger than the strongest magnetic fields on Earth. And this can lead to some crazy effects. It can distort atoms into these elongated cylindrical structures. It can distort the vacuum of space itself to turn it into a sort of refractive medium. So light passing through a vacuum will refract and distort due to this high energy magnetic fields. We also get starquakes, like super energetic Earth. Found yesterday while reading about magnetars is that if we were to place a magnetar halfway between the Earth and the Moon, then the magnetar's magnetic field would strip all the credit cards on the surface of the Earth. I don't know what the practical application of that fact is, but maybe, like, just in case, carry some cash in your wallet from now on. You never know. But with these neutron stars, we also have our favorite dead stars, the black holes. And magnetic fields are instrumental in not only feeding these black holes, but also generating this high energy emission around the black hole. So as a star collapses into a black hole, it leaves behind this disk of plasma around the black hole. This is known as an accretion disk. So accretion is the process by which this plasma is sucked into the black hole itself. And so these accretion disks are filled with these strong magnetic fields that almost serve as a pipe or a conduit for channeling this plasma down into the black hole. And right at the inner edge of the accretion disk, these magnetic field lines are twisted up to such a degree that they form these what are known as relativistic jets of light and radiation and hot matter that just gets blasted out into interstellar and intergalactic space. So not only do these magnetic fields feed the black hole, they also allow the black hole to burp and throw up the material millions of light years away. Now, another really interesting fact about magnetic fields around black holes is that there's this fundamental theorem in general relativity called the no-hair theorem that implies that black holes themselves cannot host magnetic fields. All the magnetic fields we're seeing in this diagram are anchored to the accretion disk, not the black hole. But this leads to a bit of a contradiction because if the star that created the black hole is teeming with magnetic fields, then how does this black hole shed the magnetic fields that it's born with? So this is a very recent area of study pioneered by a few grad students here at Columbia. And they came up with this fantastic name for this process called black hole balding, whereby a black hole sheds its magnetic hair. We have not yet observed balding, but we should be able to see some high energy particles ejected from this balding process. Amanda was saying that astronomers are not good at naming things, but I think this is top tier. Great. Okay, so I think we've covered everything we can on the stellar scale. But that's not it. We can zoom out a little bit further and look at our galaxy as a whole. Our galaxy is also teeming with magnetic fields. The galaxy is not just stars, it's not just dust. There's magnetic field and plasma in between each of the stars. So here we have a 2D projection of our Milky Way's magnetic field structure. And we can see that it's very strong in the midplane, but also very loopy and very turbulent as we move away from the midplane. We were able to map this by looking at interstellar dust grains, these little flecks of metal in between stars. And we were able to get this projection, but actually it's still an open problem as to what the actual 3D structure of our Milky Way's magnetic field is. And this causes some issues I'll talk about in a little bit. But the most important aspect of these interstellar magnetic fields is that they are key regulators of galaxy evolution. For one, interstellar magnetic fields enable star and planet formation. Here I show these star-forming clouds and the beautiful pillars of creation. And as these clouds collapse and spin, and they become dense enough, they form stars and eventually form planets. But an issue is, as these clouds are spinning and as they're contracting, they spin faster and faster and faster and faster until eventually, if there's nothing to break that rotation, the clouds will just tear themselves apart and we get no star formation, no planet formation. But here's where the magnetic fields come into play. I drew these two. Graphic design is my passion. And these magnetic fields, with their pressure and tension, slow down that rotation and allow stars and planets to be born out of these clouds. Another way rays are these very high energy charged particles that sort of bounce around inside our galaxy. And they're a major source of pressure, so they can push it against the plasma in our galaxy, push it out of the galaxy, they can destroy star-forming clouds, they can drive turbulence that promotes star formation. They're major components of galaxies and galaxy evolution. And if there weren't this magnetic fields in the galaxy, these cosmic rays would just stream right out of the galaxy. They'd be formed, they'd be ejected, they'd escape, they'd do nothing. But because of that complicated field structure we saw 2 slides ago, these cosmic rays just ping-pong around the galaxy for billions of years, allowing them to significantly influence the interior structure of the galaxy. Embarrassingly, we still don't actually know precisely how these cosmic rays bounce around the galaxy for a number of reasons. One of them being we don't know exactly what the magnetic field in our galaxy looks like. So this is a major open problem in the formation and evolution. But, you know, this was a 4:30 a.m. thought after a 30-minute nap. So what stand-up comedian and energetic charged particle starred in Everybody Loves Raymond's? It's Cosmic Ray Romano. So, yeah. Right, okay, let's go further ahead. So let's zoom out a little bit more from the galaxies. Galaxies do not exist in isolation. Many galaxies, like our own Milky Way, exist in these galaxy cluster environments. All of these little elliptical or ovoid shapes in this photo are galaxies in a cluster. And we see in the center of this cluster this glowing spheroidal emission. That's due to magnetic fields and hot plasma in what's called the intracluster medium, the medium between the galaxies in this cluster. And what this plasma and magnetic fields do is they control basically everything about the flow in this intercluster medium. They control how the plasma moves and mixes and cools, and this determines what matter can fall into galaxies and fuel star formation. It controls what can escape from galaxies and possibly stop star formation. So we saw before that the interstellar magnetic field controls galaxy evolution from inside, but now this intracluster magnetic field also controls galaxy evolution from the outside. And now we can zoom out the furthest that we can zoom out. On the largest scales, we get these galaxy clusters. If we zoom in, we'd be able to see individual galaxies in the intracluster medium. But also in this web, we have these long, thin filaments, which also have magnetic fields, that channel gas through the filaments into these galaxy clusters and into galaxies. But where else in this photo could we find magnetic fields? I'm getting an answer from over here. Or gaps in between the web. So we call these cosmic voids. They're the largest structures in the universe, the most empty structures in the universe. They can have densities as low as 1 proton per cubic meter, which is kind of insane. That's around 10 to the 27 times less dense than air at sea level. So there's basically nothing in these voids. So can I get a show of hands of people who think there aren't magnetic fields in voids? Okay. I thought I'd trick you, but... Oh, sorry. If you don't think there are magnetic fields in these voids, because there's basically nothing in these voids, so how could we have magnetic fields? Raise your hands. Okay. Yeah. Remarkably, despite these voids being very, 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 very empty, we still find magnetic fields in these voids. And this is baffling, at least the question. Created. Were they of primordial origin, generated right after the Big Bang by some exotic process? Are they of astrophysical origin, generated by some more commonplace plasma process much later on in cosmic history? So this is the topic of my thesis, which I'm supposed to defend in a few months. So I'm happy to say that the answer is we don't know. But what I can tell you is that magnetic fields are everywhere throughout the universe, and they do shape our cosmos on all scales. So, thank you. Happy to take any questions.
Okay, Ryan, if you'll advance the slide. So there are 2 ways you can ask questions. You can raise your hand, or you can submit it on our Google Doc. I'm going to be multitasking. I'm consulting with our weather team. Turns out the more apps you consult, the less certain you are about what's going to happen in 30 minutes. Okay, but let's get a question for Ryan. I saw your hand. When did they discover magnetic fields?
That's a great question.
So, I actually don't know the answer to that, but my guess would be maybe we started caring about magnetic fields in outer space maybe in the mid-20th century. Before that, we just considered all the gas in galaxies in the universe to be electrically neutral. And this is a major problem that led to a lot of miscalculations. But this brilliant physicist named Hans Alfvén, who also is the namesake of my cat, pioneered the study of the interplay between magnetic fields and plasmas out in space in about the 1940s. So he won the 1970 Nobel Prize in physics for this discovery. So the study of astrophysical magnetic fields is actually pretty young, considering how long we've been studying outer space.
The first question online is, what is the name of your cat? So I'm very glad that you've already covered it. Okay, Angie. If the Earth stopped rotating, would the magnetic field vanish?
Yeah, excellent question. And the answer would be yes. Because part of that dynamo process, we need both convection in the core of the Earth, and we need rotation. Ultimately, we need to generate turbulence in this fluid. So if the Earth were to stop rotating, then we would not get, that turbulence would not be able to wind up the magnetic fields, and those magnetic fields would disappear, our atmosphere would disappear, and as I said before, we'd become what scientists call toast.
Okay, question here. How do we know that there are magnetic fields in the void?
Also an excellent question. So our main evidence for magnetic fields in voids are these, right. So I said that these accretion disks around black holes can fire out these super energetic jets. There's a class of black hole called a blazar, where the jet is directed right along our line of sight. So we get a lot of high energy light and radiation from these blazars. So these blazars exist at very, very long distances from us, millions to billions of light years away. So we've been able to model the emission we expect from these distant blazars. But when we actually observe the emission from these blazars, we find that there's a major component of the light that's missing. And what we've concluded is that as the jet and material from the blazar moves through a void, the magnetic fields in the void deflect that radiation and some of that plasma. And so that's our best guess for why we're missing that component of the radiation. So this places a lower bound on the magnetic field strength of the voids. So we don't have a precise measurement, but we know it's at least 10 to the minus 15 Gauss, so about 10 to 15 times weaker than Earth's magnetic fields. So extremely weak, but there nonetheless.
Question?
What happens to the losses of magnetism when the magnetic field breaks? You showed the slide that the magnetic field was breaking.
Yeah, what happens and what happens to the magnetic field line when we see it break?
What about the losses of magnetism?
Yeah. Also an excellent question. So Gauss's law of magnetism is still conserved. It still applies even when the magnetic fields break. So what's happening is that, so if we assume the plasma to be a perfect conductor, one of the consequences of this is that the geometry of the magnetic field embedded in the plasma cannot change. But in any plasma, there's a little bit of electrical resistance. So it's not entirely perfectly conducting. So in regions where we have more electrical resistance, we can change the geometry of the magnetic fields. So yeah, in this magnetic reconnection, we have these magnetic field lines that are flowing into regions of higher electrical resistivity. And so in these regions, magnetic fields dissipate just a little bit. Some magnetic energy is turned into heat. Some of it turns into accelerating particles. And we end up with these newly connected field lines that are overall a bit less energetic than they were before. So Maxwell's laws still apply, but we're now converting some of that magnetic energy into other forms of energy. And that's how we get these explosive solar flares and coronal mass ejections, because this magnetic energy is being converted into the kinetic energy of plasma that then shoots out from the sun towards the Earth.
I'm going to
Yeah.
say one from online. Could the magnetic fields in space be helpful for human spacecraft travel?
Yeah, so I actually think, so I saw something like last week, or whenever the Artemis stuff was going on, that, like, I don't know how serious this is, but I think people were trying to build technology to surround like space capsules with a self-generated magnetic field, so that those space capsules are shielded from solar radiation, just like our Earth's magnetic field shields us from solar radiation. So ultimately, magnetic fields can help us with space travel, because the main enemy of space travel is that constant solar radiation, like those flares, the solar winds. That's what's really harmful to astronauts. So we have some way to shield our astronauts from that radiation, from that plasma, then that'll really help us with space travel. So if we can find a way to generate these magnetic fields, magnetic shields for space capsules or rockets or something else, then that
I didn't totally understand the last slide that you showed with the purple web. Can you explain that a little better? And I thought that was the magnetic field, and so the dark spots therefore would be the magnetic field, but can you explain that?
Yeah, so this picture of the cosmic web and voids, can you go over that, and what does the color actually refer to?
Yeah, excellent question. And sorry for the confusion. So this is, the purple stuff is showing gas and plasma. The brighter the region, the more dense the plasma. So in the brightest regions, those are the nodes where multiple filaments connect. Those are the galaxy clusters, where we have an overdensity of plasma and magnetic fields and galaxies. But despite us living in these clusters, despite most of the mass in the universe existing in these clusters, there's still a lot of other stuff going on between the clusters. So all the purple stuff is still plasma, is still gas. That's what this is showing. There are magnetic fields that trace this gas as well. But just because of the color bar, the color contour here, these voids are effectively black because of how underdense they are, how little stuff there is in there, how weak the magnetic fields are in there. So actually, it could be, you'd probably get a very similar map if you were to map the magnetic fields on these large scales. But this in particular is just gas and plasma.
Yeah, and I actually have a cool picture of what Manhattan might look like if we try to map it in this way, so I can show you after. We're getting such incredible questions. I'm going to end with 2 online. We'll give Ryan a mini break, and then you all can bother him after. Give him good practice for his PhD defense. But there are 2 questions I want to end on, and of course I have to find them again. What is the most mind-bending fact about magnetic fields that you did not mention tonight? What have you been keeping from us?
I tried to be pretty thorough. Can I get back to you on that?
Sure. The last one, and again, you can ask him some more questions in a little bit, is what is the day in your life like as an astronomer? Especially as a grad student, what does that look like?
Excellent question. A lot of sitting at the computer. All of the work I do is based on computer simulations. So one of the tricky things about modeling the magnetic fields in these voids is that observing any stuff in these voids with telescopes is very difficult. So really the only observational evidence we have is from those blazars. So what we have to do is basically run experiments on our computer via simulations. So try to form the universe from its earliest stages, go back, tweak some parameters about the early universe, and try to see what matches up best with what we do observe. So a typical day, there's running simulations, there's analyzing the simulations, there's taking naps while the simulations are running. But yeah, for my research in particular, I use two different types of simulations because these large-scale, what are known as cosmological simulations, that simulate the whole universe. So like this image of the cosmic web comes from one of these cosmological simulations, where it's simulating these scales of millions or hundreds of millions of light years. Those are great at modeling the cosmic web and the voids as a whole, but they make a ton of assumptions about the plasma and magnetic fields in this matter. So I need to pair these with these very, very small scale simulations that treat the plasma and magnetic fields from first principles, and then I need to try to interpolate between those small plasma scale simulations and these large scale cosmological simulations. So yeah, it's not as glamorous as you might think. It's a lot of fussing with code and Linux and getting frustrated and taking more naps when I'm frustrated. But yeah, great question.
And hopefully not all of it involves 4:30 a.m. slide making.
Often, but not always.
And if you're not annoyed at your simulation, you're annoyed by the weather. So it's annoying for both sides. All right, let's give another round of applause to Ryan. We're gonna do a raffle, and then I'm gonna let you all go. Unfortunately, the weather is not good enough for our telescopes to see through the cloud cover. Hopefully in the summer we'll have much